this video, we're going to look at an application of calculus with what are called the differentiator and integrator circuits, also known as the high-pass filter and low-pass filter. In Calculus 1, two of the main concepts we learn are the derivative and the integral. In essence, the derivative models the rate of change of a function with respect to its independent variable, and while there are many things we can learn about a function by integrating it, the integral can also be seen as a way to undo the derivative of a function. With function notation and ignoring constants of integration, we could say if the derivative of f of x is g of x, then the integral of g of x is f of x. Let's see this by starting with a simple picture of a graph that we'll call f of x. This function is made up of two lines, and it is a snapshot of what we call a triangle wave. A triangle wave is one of the many waves that can be an output of an oscillator. An oscillator is a sound source of a synthesizer that is the result of electricity passing through a capacitor. Let's hear a triangle wave and see its representation on an oscilloscope. What we're now going to do is differentiate this triangle wave. Let's consider again the graph that we drew above. It has two lines that make up its shape. As we look at that graph from left to right, the first line has a positive slope. It goes up and to the right. And the second line has a negative slope. It goes down and then to the right. The derivative of this graph would then be represented as a graph that has two parts representing the two different slopes that are on that triangle wave. One part of the derivative would be a horizontal line representing a positive constant, and then another part would be a horizontal line representing a negative constant. We can actually draw something like that below. This graph also has a wave named after it, a square wave. Let's see what that square wave looks like and sounds like. So what we will do now is start with the triangle wave and differentiate it with what is called a high-pass filter. Most sounds have many frequencies or pitches that make up its total sound. What a high-pass filter does is only allow the frequencies above a cutoff point pass through. When I turn a dial that corresponds to the cutoff point, the sound will start to become very thin. So that's what it sounds like to pass a triangle wave through a high-pass filter. Now, let's differentiate this triangle wave and set the cutoff knob so that when we see the wave on the oscilloscope, it starts to look like a square wave. So now while we have this sound going, I'm going to take this approximate square wave and then integrate it. I'm going to undo what we just did. But the way that I'm going to undo that is by running this current sound through what's called a low-pass filter. This does the opposite of a high-pass filter. It only lets the low frequencies pass through. So this is starting to look like a triangle wave, and to get a better idea of that, I'm going to zoom in on this picture. So we started with a triangle wave, differentiated it, got an approximate square wave, and then integrated that shape, and now we're back to where we began. Now that you've seen the mathematics behind these filters, you might be curious about how they are used. You're going to hear an example of the same phrase repeated 3 times. The first time, there has been no filtering. The second time, there has been high-pass filtering. And the third time, there has been low-pass filtering. Integral of g of x is f of x. Integral of g of x is f of x. Integral of g of x is f of x. Integral of g of x is f of x. Integral of g of x is f of x. Integral of g of x is f of x. If you put these two filters together, you can get really complex sounds, like this.